Am I audible? Okay. So, good afternoon, everyone. Today is the week 10 interaction session of the course Reliability Based Structural Design. So, my name is Devasis Panda. I am a research scholar and Prime Minister Research Fellow at IIT Guwahati. And for this July-November 2024 semester, I have been allotted to this course as PMRFT. And this course is instructed by Professor Arunasis Chakraborty, IIT Guwahati. So, today we will discuss on metamodel based reliability analysis. So on the last interaction session, we have started this metamodel based reliability analysis where we solved different problem using response surface method. So today we will move to moving least square method and we will see how to solve different reliability problem using moving least square based response surface method. Then we will move to stochastic response surface method and adaptive stochastic response surface method. So more or less these concepts are similar, but we will see how we can work out different kind of reliability problems using these methods. Okay, so let's start quickly. Like, before going to that moving least square method or moving least square based reliability analysis, let's quickly revisit what we have done on the last interaction session when we solve different problem using response surface method, right? So basically why we need that metamodel based reliability analysis? The answer is like, when we don't have our limit state function gx that is not completely defined with respect to the basic variables, like the gx can be x1 x2 minus some moment like 1140, like that cantilever beam problem we have seen. Here the limit state is defined explicitly with respect to the basic variables. That means we can have the gradient and solve the gradient based reliability problem. Now when we don't have this limit state in uh, explicit form or explicitly defined with respect to the basic variables, then what we generally do in response surface method, we first propose some response surface. Say instead of gx we propose some rx, that should be some polynomial function using like a plus say b I xi plus, you can increase the this polynomial, like you can have linear feet, quadratic feet, cubic feet, we have seen this. So c say xi square. Then what we did, like we solve for the coefficients, and once we solve for the coefficient, like we solve this coefficient using least square approximation. So we will go into it quickly, least square approximation, and then once this limit state surface is ready or the response surface is ready, we perform the gradient based reliability method. So quickly, let's quickly go through that code and that algorithm, and uh, quickly try to figure it out why we need that moving least square base response surface method, while we have the response surface method where we solve the coefficient using least square approximation. So least square approximation, in least square approximation what do we do? The least square approximation is nothing but a statistical, we already have discussed and solved problems, or even we code it. If you see the previous interaction video, you will find it out the codes. Like we'll just go through it quickly. We have like least square method, what we generally perform in least square method, we consider some polynomial function, and then what we do with respect to the actual design, actual points or actual experimental points, what we have, we need to estimate the sum of square of error, and by this way we have the number of normal equations as much as or as many as the coefficients are there, and we solve for that unknown coefficients and we get that least square method. The matrix for that equation in matrix form, we have that a is equals to nothing but x transpose x inverse x into f, that original function. So like how this response surface method goes, let quickly touch it, then we will move forward why we further need that moving least square base response surface method. Now in moving least square, nothing but like least square we solve here using this. Like when we consider the least square solution, we need to first consider some basis function. So we perform this using the basis function itself. But for moving least square technique, like on the previous class, we have seen that weighted least square. Same thing is that moving least square. We introduce some weight to the basic function, and the final equation for solving the unknowns we will have in this format, right? So we will come to it little later, like why we need that moving least square technique. First, just go through like what was the response surface method, how we perform that response surface method, like why we need that meta model based response surface method. We have already discussed, like when we don't have our limit state explicitly defined with respect to the basic variables, then we cannot perform the that reliability based, that gradient based reliability analysis. So we need first approximated gx, and then we uh, perform the reliability analysis on that. So what was the code for it, or what was the algorithm for it? Like first we define the random variables, their distributions, and then we considered some rx, that means response surface. And that can be, if you wish to fit a linear response surface, then you just need to take that first two terms. If you wish to fit cubic or quadratic or cubic or higher order term, as per your requirement, you can first set that response surface. So say rx is equals to a plus b1 x1 plus, say we will go up to quadratic approximation c1 ci xi square. Now what we need to do, we have the response surface in terms of some polynomials. First, we need to solve these coefficients. So for this solving these coefficients, we need to generate that 2n plus 1 number of support points. That means from the support points, we will have that much of normal equations, and we can solve it. So first approximation was the mean, and then we need to consider, or we need to take the support points in and around mean using mu plus minus k sigma formula. So once we generate these support points, that means we have 5 support points, and here we considered up to the quadratic approximation, then we can easily solve for the unknown coefficient. Now once we solve this unknown coefficient, we will have our response surface ready. That means once we solve this coefficient, we will have something like this. Say we will have some value of a, say 1.11 plus say 1.20 into x1 plus something 3.32 into x2. Now once we have the response surface in this format, we can now apply the gradient based reliability method. So first we need to define the random variables with respect to their distributions. Then we need to consider one response surface or meta model, which will replace, or which will be actually the replicate of our actual response surface. And then we generate 2n plus 1 support points and solve for the coefficient. Once the coefficient are solved, we can have the response surface ready. Now we can apply the form first order reliability method or gradient based in method to solve for the design points xd, and these design points will be on the response surface. So here you can see this will be your response surface, and if you solve for the solve using the gradient based reliability method and look for the beta and the design points, you will get the design points on the response surface itself, right? So obviously these design points will not be on your actual limit state. Now how, this question, how you can identify whether your limit states are on the actual surface or not. So what you need to do, now you have the xd, that means the design points in your hand. Evaluate your gx using this xd. Now, if these design points are on the limit state, then your Gx evaluated using that XD will be 0. That means you can conclude that, okay, my design points are on the limit state. But for this case, obviously it will not be, because the design points are on the response surface. Now, what you need to do on the further check, when you evaluate gx and see that, okay, my gx is not equals to 0, that means my design points, evaluated design points, are not on the actual limit state. What you need to do, then you need to perform one linear interpolation with respect to the mean point to get the actual design points. Now it's simple linear interpolation. You have 3 points. Like first point will be your mean, second point will be the actual design points, that means xn, and third will be your xt. And now you need to perform the linear interpolation based on these 3 points. So you will get basically this equation. Like you will get this equation. Nothing but this comes from the linear interpolation. Like when you perform the linear interpolation, your g of xn will be 0. Like if I show you, this will be your, say for example, here, say let's say we have xd first mu points. This is my starting point of the interpolation. So for respect to mu point, we will have our g of mu. Now for the design points on the response surface, we will have g of xd, and for xn we will have g of xn. So we need to find out, or we need to interpolate with respect to that xn points, right? That what will be my this point. So you can put it like this. This will be your x and y, and this one will be your x1 y1. This should be your x2 and y2. Now just do it, like y minus y1 and, or x minus x1 divided by y minus y1. You can do it like that also. So x minus x1 divided by y minus y1 is equals to x2 minus x1 divided by y2 minus y1. Now replace all these values. What will you get? Like if you replace this, you will have here uh, x minus x1, and your x is nothing but your xn points minus the x1 will be your mu, the mean, divided by, say for example, x2 minus x1. I am here trying to get in that. So x2 will be your xd minus x1 will be your mu, is equals to, on the right hand side you will have y. So y value we set for, like instead of x and y, just flip it. So you will get same thing, because left hand and right hand side are same. So you will have like x we have done. So y minus y1, and that is the g of xn minus g of mu divided by your g of x. Then you will have y2 minus y1. So y2 will be g of xd minus g of mu. Now here g of xn, ultimately my final design points will be at the limit state. That means g of xn will be 0. And now if you simplify this equation, you will get xn in terms of this. That means you need to perform one more extra steps to get your design points, or to make your design points on the actual limit state surface. Now once this exercise have done, obviously new design points will be on my limit state. So obviously when we evaluate again the gx, we will get gx equals to 0. And then we can evaluate the reliability index using that uh, estimated points, or that final points. Now we can perform the reliability analysis for different kind of problems using this method. Now we have seen that on the last class we have solved this using MATLAB code, and we have seen that the results are satisfactory. Now the thing is, why we need that moving least square based response surface method. So the first thing, when we perform this response surface method globally, or when we have complicated shape of limit state function, then using this response surface method, using normal least square approximation, we will have larger modeling error. Now the thing is, how we can minimize this larger modeling error. Now why this larger modeling error will come, and all these things I will show you in a minute. So the thing is basically when we try to approximate using ordinary response surface method, using ordinary least square technique, when we try to fit it globally, then we may have bigger errors. Now bigger errors due to what? Due to what? That we will see. So in moving least square method is nothing but like we have solved this problem using response surface method. Already we have discussed it. So I will go into it a little later. So weighted RSM actually based on the moving least square or weighted least square method, where weight is introduced to your basis function. Now weight can be different, and basically this weight is controlled by the users who is wish to uh, locally approximate these points or these points and these points, so completely based on user. Now here this introducing these weights actually helps in minimizing the local errors, or we can say introducing these weights, by introducing these weights we can have better local approximation. Now this phenomena we have seen during our last class. Like for this example, look at this. Like we have two data sets of 1 2 3 4. So for number of x and y, these are the observations. And when we perform normal least square method by ordinary least square method without any weight, so we have this blue line, right? So here we have seen that okay, for this point, that means for the third point, we don't have the better fit. So what we did then, we introduce one weight for this particular location, and have seen that okay, my local approximation, here you can see the red line is the weighted least square approximation using a particular weight we have assigned for this particular data. Now we have seen okay, my approximation get better. Now if we, so it's like arbitrary weight. If we increase the weight further, what happened? Like next we have seen that if we increase the weight to 100, so we have seen my, for this point, so look, I have only introduced or apply the weight for this particular point. So obviously here we can see that we have better local approximation. Now think, if I can perform this for all the points, then obviously we will have better global approximation. So the concept is very simple, like introducing some weights and get better local approximation, and which will eventually lead to the global better approximation. Like if we further want to clear this concept, here you can see this example, or look at this example. Like here, one second, like I just need to pause it for to to tell you like what is the cursor. Like here you can see this is the, like I need to pause it, but I'm unable to now use the cursor. Yeah, it's appearing. Great. Yeah. So now here you can see this is actually your actual limit state function. Now see, your response surface or is a complex kind of wave function. Now if I or you want to perform a fitting, or you try to fit some polynomials using basic least square approach, we will not have the better fit. So here what we have performed, like we do the local approximations using the weight function and some support points, and look, in each and every points we are approximating or locally approximating the function, and globally we will have the better fit. Like each and every point, look, each and every time step we are doing the or each and every points data points we have, we are approximating the local approximation and getting the better results. Like now for this response surface, if we wish to fit some polynomials using uh, that normal least square approach, then we will not have the liberty to get the better fit. So here in weighted least square or the moving least square, we introduce some weight, and with respect to this weight and some support points, we do the local approximations. And once we have all the local approximation, we can globally have our you know response surface fit in a better way. So the concept is very clear here. You just need to control your feet by using some weights and some support points around, that for the local approximation you need to perform it. Now this phenomena can be explained using this also, like when we, yeah. Now, when we perform that ordinary least square method, we have seen that most of the coefficient globally they are constant. They cannot vary because for different points we are not introducing any weights to vary the coefficients. But in the moving least square technique, we have a better and wider range of the coefficient. We just need to select them with respect to some weight function and support points. If we can, then we can have or we may have the better fit for our uh, that response surface problem. So the basic thing is the moving least square or that weighted least square base technique basically, or the convergence criteria for these techniques are two. Like first thing, you need to perform this local approximation using some weight function. That means you need to choose the weight correctly or properly as per your requirement. And then comes to the selection of the support points. Like in response surface method, we apply the selection of the that selection of the support points using mean and mean plus minus k sigma, and we get our support points. Now here we have different process for selecting these support points. And here the design of experiment, actually in design of experiment we select or that support points and the zone of these support points we define here. So here, like least square approximation or RSM, we have seen that we use the scheme for the selection of support points mu and mu plus minus k sigma. Here we have different kind of DOE as per your requirement, as per your problem statement. You can select different kind of support points and check. Like for Khosal design, we have for linear basis we have 3 support points. For quadratic basis we have 4 support points. Now, if we move further, we have full factorial designs. Full factorial design, we have for basic, linear basic, we have 4 support points, and quadratic basis, we have 6 support points. Now, D optimal, it's nothing but 1.5 times of the Khosal design. And we have CCD, central composite design, where central axial and box, these three are combined, and we will get the support points. So there are different support point generation scheme are available. Like the basic concept why we need to different scheme of support points, the basic thing is like you need to have the better approximation. So two things we need to control: first, which kind of polynomial we select; second, okay, what should be my weight function to get this basic fit. And now to with that weight function and with that polynomial, if I wish to get best fit, then what should be my design of experiment methodology. That's all. And this will vary with respect to different problems and different type of analysis you are performing. So the algorithm is very simple, like similar like your response surface method. But here, like in response surface method, we generate the support points in considering mean plus minus k sigma. But here we can consider or we may consider different kind of support point generation scheme. And the support point generation scheme should be such that will cover the domain of interest. So first you need to define some initial center point or the domain, or we can say search domain, like which kind of polynomial you want to work with. based on that you can select your domain. Now once the domain is selected, then generate the support points. For generating the support points, you can check with your different DOEs, like which support point generation scheme actually best for your purposes. Then evaluate effects using that support point, and once we can evaluate this, our response surface method is ready. That means the polynomial is ready. Now we need to define, or we need to determine the coefficient. So obviously we are doing here moving least square method. So obviously using moving least square technique, we will find the coefficients. That means we introduce weight and we solve for the coefficient. Now once these are done, we can go with the optimal point solution. Now if this is converged, so we'll get the optimum point. If not, then we need to perform this exercise again by reducing our domain of interest, and then again we will check it. That means in a way this is similar to your response surface method, but to get the better fit, here we control the weights, the support point generation, and we are trying to fit it locally so that we have ultimately the better fit. So this is in a way the algorithm for the moving least square approach. Now what was the algorithm for the least square approach? That means using least square approach, RSM based least square approach. Here nothing but the generation scheme is simple: mu plus minus k sigma. Mean is the center point, and finally you just need to perform one uh, interpolation to get your design points on the response surface. So basically these are similar kind of things. Now let's quickly go through one example and then code it and check whether these are giving the results or not. Like here we have this cantilever beam problem. Again, fyz minus 1140 here we have. So what we need to do if we wish to perform using weighted response surface method? So what we need to perform? First we need to select one weight for this one or two weights. What you wish to do, you can select different weights for different variables as per your requirement. Now choose the weight, then support points, generate support points using support point generation scheme. Get your response surface ready. Once your response surface is ready, now you can perform different kind of reliability analysis. Like during your course, Arunasis sir has shown you how to perform, form first order reliability method after getting your response surface. Even when your that Rx is ready using that weighted RSM, that means after solving the coefficient using using moving least square approach, you will get your Rx ready. Now once you have Rx ready, your Rx is ready, then you can either perform Monte Carlo simulation or different form or SOM based on your approach. So today what we will do, we will perform the Monte Carlo simulation on top of the response surface which we have actually generated using weighted least square approximation. Here, so we will solve this problem, and also we have one another problem. It's like Frank's function. So it's a hypothetical limit state, and this function actually used to validate different kind of model. So here also we have use this Frank function to check the different kind of reliability results. So here also we will perform this and we will see that okay, my here also you can see for this problem the results are very similar. Like if we perform this using, because this is in explicit form, we can easily perform the first order and second order reliability analysis using Hasselbalch reliability index concept or directly using the Recowitz algorithm. Then if we use after getting the response surface, if we use form on top of it, we will get this result. So these are like very close. Now if we perform the MCS with suitable weight and proper number of simulations, we will get 3.61 results. And for this also we see that we are getting the similar kind of results. So what are the basic difference between response surface and this weighted response surface? Is nothing but in a response surface we are globally approximate the the whole total things. Now here in weighted response surface we introduce some weight, we introduce some DOE scheme, and we are trying to get better fit for the different response surfaces for our reliability analysis. Okay, now let's quickly go to the MATLAB and try to figure it out how we can code it and check the results. Okay, so Abdul, you have done it, these things.
Yeah, I've done it.
Okay, so let's quickly go to it and check. First, let's go to this RSM once again, and then we will see MLS RSM. So the concept is very clear. We are getting the best local approximation. So local approximation, for the local approximation, even you can also propose some support point generation scheme. Okay, if you wish to follow this support point generation scheme, your result, we will get these results, or other, like weight, what should be my weight, customized weight one can use. But at the end of this exercise, you need to validate your thing with some results. You make a results, MCS is there, you perform MCS and you can check the results with them. So this actually depends on the nature of the problem, and different kind of editions have already done, like okay, this, and still this is going on. So this is like topic of research. If someone interested go into deep, they can, but like for me, my domain is like quite different. I actually work uh, with the turbines and nonlinear, the control and identification and modeling part. So yeah, the random vibration and my work is similar, but still this kind of reliability analysis also, if you want to wish to, like you are modeling something on also you use that meta model based thing. So you need to have to use some basic function, some polynomial. You said that you use that
Yes.
polynomial chaos based expansion for
Yeah.
your this
Yeah.
thing. You are using the Hermite polynomials for your uh, purposes. So for the Hermite polynomials, we have the roots already, so we can generate the support points and uh, do our design. So
I
like
had a question, if
yeah,
if I'm allowed. Actually, I was thinking if we have, for example, if we use polynomial cross expansion as a surrogate model or a meta model, fine.
yeah.
So why do we go for form or SOM based analysis? Why do we not directly go for MCS?
Yeah, we
Any,
can we can go, like I today I will perform the MCS. I love that
yeah,
MCS, but the thing is, in MCS the problem is, what is the problem? That n.
the
uh,
number of points, right?
yeah,
But
for example, arbitrarily you perform this and choose some n, okay, say for
okay.
10 to the power 6, and
Mhm.
now change this 10 to the power 8. Now how you can conclude, okay, my this n is okay? Once you have the probability of failure confidence interval, you have some formula, okay, this formula giving me
Uh-huh.
n and this is my
Okay.
result. You have some logic.
Okay.
But abruptly you perform uh, like
Out of nowhere. Yeah.
yeah,
Got
not out of phobia, like okay, you think okay, this can be or this might be, not out of phobia, you are in a stage, good stage, okay. So
it.
you
Uh-huh.
will not perform abruptly, you will give
Yeah.
some good reasonable reason, but still the question is with what you are
Okay.
validating your results.
Got it.
That's why
So,
we need form.
so if I can take one more minute, I had a question. I mean, this is basically an idea what I'm working on.
Yeah,
I was planning to do the conventional FORM test, I mean FORM analysis on my problem,
yeah,
the SORM analysis, and then I'll go for MCS, but I will find MCS points on 2 to 3 locations only, not the complete range which I wish to
yeah,
simulate
yeah,
basically.
no, no, no,
And
not necessary. Yeah,
then I can use this meta model and use MCS using this meta model
yeah, on top of this.
and compare all of them, and
Yeah,
then say that FORM, SORM, MCS, you can simulate all this using PC based
yeah,
MCS or
PC based FCS, yeah,
yeah.
and check the results. What you are getting the results, but it's like it will be iterative process. You need to check it, check it, check it. Then
Yeah.
once you convergence is achieved, okay, these are the ranges. Now I
Uh,
can conclude. Like, in a one go, these are not done. Like so,
this
you need
yeah.
to iteratively. But the idea is okay. You can perform it. But the thing is, yeah,
Uh,
directly you can perform MCS, but there is a dilemma. Okay, you need to have some method to establish
uh,
your results. Yeah, that may
exactly.
be error may be there, no problem with that. Like we already have 5 to 10% error with MCS and closed form solution, we have seen it. And
Fine.
we can improve the MCS, like we have sequential MCS also,
True.
sequential Monte Carlo simulation, stochastic Monte Carlo simulation. We have like few days back, I work with some pharmacokinetics model. where
Uh-huh.
they have used sequential Monte Carlo simulation, right? Like
Okay.
they solved this transitional probability, that Markov process you have went through the
Huh.
Markov process.
Yeah, Markov chain.
Yeah, sort of like that.
Uh,
So and also just I went through the paper to solve this stochastic differential equation for that only, but I have seen that okay, that also can be done. But reliability, actually in my domain, reliability thing is not here, but I am planning to add the reliability thing. Why not? Like I have also my model, so I will perform the reliability also.
True.
So it's also same thing I will do with my turbine. That means not only for a whole turbine, for some structural response I can easily perform. And yes, that same thing, you have some model with you on stroke stability, I will have some nonlinear model of my turbine, like control model or
True.
anything, the tower vibration model. Okay, so
Mhm.
we can perform the same thing for these two things, like same thing. Yeah, this is an idea I can also, but I am actually working on the modeling part and in nonlinear dynamics, so I haven't thought of adding that reliability thing, but it can be easily, right?
Easy. Yeah.
It easily can be. Yeah, I will also, and you can contact me, no problem. Same thing I will also perform on my model. I have
Yeah.
different models, all like 2 3 models, so I can also check which is better.
Sure.
And if we can propose some other support point generation scheme, yeah, we can do it. And when I'm doing this course and all the codes with me, why not? Yeah, that's a good idea. So you, what you are doing, I can also replace with
Yeah.
my
True.
work. Yeah.
Let's see. I'll try and email you as soon as
Yeah,
possible. You
yeah,
have
yeah,
confidence
yeah.
in
No
IIT
issue.
Hyderabad.
We can discuss, and
We will
the
discuss.
thing will get accelerated quickly. We
Okay.
can solve this problem. Like, what do we
Sure.
need to do? The concept is ready.
Exactly.
Model, if not, you can ready your model. Now you need to code this thing. So basic structure are ready. We need to sit for like 1 or 2 weeks. Then we will have all the conversion results.
True.
That's all.
True. True.
Nothing. Just we need to, like, what is the problem? Why we are getting delayed in our research? Like at particular point, if someone says, okay, this is this, if you are
Uh-huh.
right or wrong, if I says,
No.
okay, I
Ah,
thought, okay, I'm right, but still there is dilemma. Okay, am I right? Someone is
yes.
says, okay, yeah, this concept is right. So then you can move on and you can do
Exactly.
your work.
100%. Yes.
Yeah.
Yes. Yes.
So yeah, we will work on that. Okay, this course
Sure.
almost end, but get in touch. We will, within this month we can do this exercise. It's quick.
Actually, this week we have this a conference in IIT Hyderabad.
Okay.
So just as this week ends, as I'm the coordinator, so I have to do a lot of works outside my academics now for this week, and then we will start. Hopefully,
Yeah, yeah,
hopefully.
yeah. Because also, well, I also need to go to my hometown for the puja.
Uh,
So yeah,
Fine,
after that we can sit
but
and
we can talk on emails.
yeah,
Yeah,
different kind of reliability analysis we can perform using this. And very simple. If we can, validate all these things, then your results, no one can say anything about your
question.
results. Yeah,
Yes, yes.
and straight away it will get published. And if you
Perfect.
can solve some stochastic differential equations,
Uh-huh.
like non-linear equations, so already we can solve, we can have this in a stochastic differential form. And if you find it out, like stochastic differential sense, that means in Ito sense or in Euler-Marima or Milstein sense, very minimum work are there, very minimum.
Oh,
So we can figure it out. We will sit and
interesting.
figure it out. Then it
Sure.
will be good work. You work with your
Hope
stroke stability problem. I work with my, but the basic behind the codes, they are
it's the
simple.
same.
Yeah,
Yeah, it's
your
reliability
number
all.
of variables will change, and that's all.
The model will change at
The
max.
model will change.
Exactly.
Ultimately, your number of variables will change.
So the
Rest
same. Yeah.
thing. So we can one thing do all, we can do all the reliability analysis like form, SOM,
Yes.
then meta model base and hypercube sampling. All the
True.
thing we can check it, and okay, the summarized result. You will not get the summarized result of all the things in a one go, I think. No.
Uh-huh.
So yeah,
Interesting.
it can be a good idea. So okay, so let's today we will conclude. Then we'll discuss. Okay.
Sure. Sure.
Right. So why are we? Like we just try to code this first. Let's see how we can use it. That response surface method already we have seen on the last class. Like here, first, you need to here the response surface general code. Like it actually counts your cross term also. If you use the cross term, so it also can calculate the cross terms and give you the satisfactory results. So here nothing else. First you need to define the tolerance for your tolerance and number of iterations. Okay, this is like one check I have introduced here for different. I was trying to solve some different problems and it was like giving some convergence issues. So it's check. You don't need to worry about it. So these are the tolerances. And these are the initial support points like zeros and zeros. We need to define the lanes and all these things. Then you need to uncorrelate your variables if they are not. And if they are already uncorrelated, then you can get directly. Now, we are talking about the response surface method, original or ordinary response surface method here. One second. Yeah, so we were talking about the response surface code. So let's go into it. Like sharing 2 or 3 screen is actually little problematic. No problem. Okay, so first we need to generate this 2n plus 1 points. First point will be your mean and rest of the points will be the sub points around it. So the first point is mean. Second, the rest of the 2 points will be mean plus k sigma, and here mean minus k sigma. Once my all support points are ready, I am calling my limit state, because now I need to have this simultaneous equation. So I am calling my limit state using these regret points. Now once all is done, I just perform the matrix operation to get the coefficients. So here the coefficients are ready. Now, if you place this coefficient in your response surface or this polynomial, you can have the complete polynomial ready. Now, once we have this polynomial ready, you can now perform this requisite based algorithm or form. So here, nothing but form we have already seen. We need to convert it to the equivalent normal. First, we need to do equivalent normalization. If not, like if we have log normal, other kind of variable. So first, we need to convert it to equivalent normal. Then we need to transfer it to the standard normal space, and then we find out the different gradients and perform the reliability. So here we are finding out the gradients, here we are getting the design points. Now once we get what we have seen, once we get the design points like xd or gd, here gd, that means the limit state surface evaluated using the xd points. Okay, that xd points we are getting. Now we are getting the gd, and gm is equals to on the actual limit state surface. Now here we perform the interpolation to get the points on the actual limit state surface, and then we will check, okay, my gx is getting 0 or not, and then find out the error. That means whatever you have the set the error for your stopping criteria, it will check and it will stop. And finally, once all the solution is done, you will get your beta and pf is uh nothing but phi of minus beta. So phi of minus beta, that means phi is nothing but the standard normal variate. So normal cdf minus beta 0 1, that means we are getting the beta and pf. Now if we call if we wish to perform one example like this example, here we have the cantilever beam or the cantilever beam problem. So here we can see that the results are like, we are in third iteration, we are getting the results beta is equals to 4.2 and pf is equals to 1.01. So let's quickly check we are getting that values nearly or not. So let's quickly here look at the like inputs. Cx is 3.8 and 2.7, 38 and 54 both are normal, and we are providing initial beta as your 3. So yeah, we are getting 4.2 and 1.07, 4.2 and 1.07. So 4.2 and 1.07 and 0.1 very nearly 1.01, sorry, 1.01 into 10 to the power minus 5, similar kind of same kind of results. So what we have done in basic response surface, we generally use the first thing, support point generation scheme. Here we use the support point generation scheme as mu plus minus k sigma. Here you can see we have generated the support points using mu plus minus k sigma. Then we solve this using the ordinary least square method. Then we prepare our response surface and go for the second order reliability method, gradient based method, and solve for the reliability and get the results. Now come to that moving least square. So these are sort of the least square based technique. Now if we wish to perform the moving least square or weighted least square based approach, so in moving least square or weighted least square based approach, what we have seen that here we are doing the local approximations at each point using some weight and some support point generation scheme. And we have seen different support point generation scheme are there, like here Khosal design, full factorial design, de-optimal design, and CCD. And also other different kind of support point generation scheme are there. So first we need to select one weight function. So here we have different kind of weight function, like we have linear, quadratic, cubic, and regularized different kind of weight function. Based on this, or basically these weight functions are selected based on your nature of your problem. And or in general you can code all of this and you can check it. So precisely that have been done during this, like I have coded all the weight functions and I can check with that. So first thing in that is to generate the support points and weight, assigning weights to that particular points, and then ultimately perform the reliability using either second order, or we can go for MCS. So precisely what we will do, we will perform the Monte Carlo simulation on top of the response surface, what we will get. So first, generating the support point first. So let's see the code line by line. So first here, uh, all the initial things are given. Now here look example ID, because we here I am want to call different kind of problems or solve different kind of problem in one script. So example ID. Now DUI ID here, design of experiment. You can make a function file of your choice for this design of experiment. So all different kind of design of experiments you can try and check your results. So here 1 2 3 I have added like 3 DOE. So we can check with that. One like axial, two rectangular, and third I forgot what I add. Like now weight type, here the weight type is one for regularized, two for exponential, three for the square. Like you need to find out these weights we call from a function file, where these weights are already defined. Like here the weighted matrix. If we provide the case one, the rectangular weighted function, and this way the weights are calculated and will be assigned. This one is for exponential, this one is for least square. So you can make the list. This is not the exhaustive list, you can make it exhaustive as per your wish. Now first all these things are done, like from this para we can control our inputs. What should be the design of experiment for this particular problem, what should be the weight type should be assigned with this problem. Now what do we need to do? As per the example ID, you need to provide mean, sigmas, index. Like in your limit state, there can be different kind of variables, like can be normal, log normal, and all these things. So here index, like 2 is for normal, and we have different kind of 3 4 5 6 we can see. And index you can change as per your convenience, like which kind of random variable you are working with, because these things are needed for the for first thing for the equivalent normalization if you are performing form. And this also needed for MCS also. Why? Because you need to generate the random numbers, so you need to first have which kind of random variable you are dealing with. So here that, and in the number of variables here. So we have only two number of variables, so these two. Now what we need to do, we need to perform the support point generation scheme. So here look, the support point generation are there. So if we provide the input as 1, it will provide the support points, or it will generate the support points using the axial formula. Then rectangular points or rectangular DOE, and I think Sobal sequence. Sobal sequence actually not covered this here, but there are different kind of support point generation scheme. You can here add your CCD or CCC. Sorry, not CCD. That CCD. Yeah, CCDs. Central axial box, this also. So during your course, I think the course instructor have used that CCD, but we will go with that axial or either rectangular type. Now once we have generated the support points, what do we need to do? We need to pass the support points to our limit state function. So fval function contain our limit states. So here you can see for case 1 it's a sine function, for case 2 it's the Frank function, case 3 it's the deflection of beam, and all these things you need to provide as a weight function, as a limit state surface. Now once you have evaluated it using that limit state surface, now what you need to do? You need to perform the Monte Carlo simulation. Now here choose the number of samples you wish to perform Monte Carlo simulation. Now you can seed the you can place one seed also and perform the Monte Carlo simulation. Now at that point I am calling the Monte Carlo simulation code, and we have already seen in Monte Carlo simulation code what we generally perform. First we generate the random numbers. Now once the random number are generated, using that generated random number, we need to evaluate our gx, that how many times the gx is fall and how many time is 1. So how many times it falls, we count it, and the pf is nothing but the count, that means how many time it falls divided by total number of samples, and we will get the pf. Okay, and the random number generation we have already discussed for the MCS. Like in MATLAB, we have different random number generation scheme for normal, normal, log number, log normal, relay, and all other kind of things. We can perform this kind of random number generations. So in this code, once we have this response surface ready, so we can easily call this code, and you will get the pf and beta corresponding to our particular points from where we are studying. So here let's try to solve the Frank function problem. Like here we have the Frank function problem during your course, this. So during the course actually the Frank functions was solved. Great. So let's see, for the 2 example ID 2 is the Frank function. Go to your fval, so you can see the example ID 2 contain the Frank function. Now if you call it, so it will get the results. So let's see our code is okay or not, and we are getting the results correctly or not. So here we are getting like 2.92, and this is the support points what this have generated. So we have here selected the support point generation scheme as 1. That means it generates the support points using this axial support points or axial points generation scheme. And here are the support points which have generated using this axial support point generation scheme. If we wish to follow different kind of support point generation scheme, we can also go with that, like how we can provide that support point generation scheme and not, and using different kind of support point generation scheme and weights. Like here I am considering the weights as weights 1, that means regularized weight. You can also check your results with exponential and least square. So here we are getting the close results. Here we can see that 2.99 was the result, whatever that your course instructor have shown, because during that here 2.92 almost very close. But I can remember that during that course, that CCD, uh, the support point generation scheme, the CCD was used. That's why there was little variation in the results. And also we can check different kind of problems using this. So if we change this DOE ID, like now I wish to generate or perform the problem using like my design of experience would be 2. That means here we have the rectangular design points. So that means we have more number of points for our generation. That's why it is taking much time rather than the axial points, but it will eventually give you the results. So second, like first we have tried that support point generation with axial. In axial we have minimum number of support points. In rectangular we have, you know, more number of support points than axial. So it is calculating, it is generating the support points, evaluating your GX at the support points, and then calculating the MCS and getting the results. So here we can check like we are getting the results or not. Now we can confirm that, okay, what are the basic difference between that response surface and the moving response surface method in the reliability one. So it's taking quite good time, like when we shift from axial points to, yeah, it's generated. Now you can see when we have selected the rectangular support point generation scheme, here we can see it generated lot of the support points, but our convergence will be very good, like 3.09, very near to your 2.999. So we can check different problems using different DOE ID and different type of uh, support point generation scheme. So let's quickly go through it once again so that these concepts will get clear. First, in moving least square approximation, like in least square approximation, what we generally do, we don't introduce any kind of weight. We just perform the curve fitting technique using normal least square approach. Now in moving least square approach, what we generally do, we introduce some weight to the basis function. Now this weight. Now these weights are very helpful in localizing or minimizing the local error or getting the best local fit. Like on the previous class we have seen, just recall this example, we have 4 data sets, and first we perform the linear least square or the ordinary least square technique. We perform the ordinary least square technique, and and we have seen this blue line. So here we can see that the approximation for this particular point is not very good. Now we introduce some weight 10 for this particular point. Now we can see this red line is nothing but the weighted response surface. Now we can see, okay, we are getting the better fit rather than our weighted response surface. Now if we wish to, increase the weight more, so we are increasing the weight for this particular point. Now look at this, we are having the best local fit for this point. Now think, if we can do the same for all these points, we will have the better or the best fit. Like for this, see the response surface. This is the blue line is your actual response surface here. Now, if we wish to fit the normal, the ordinary least square method here, so we will not have the better fit. So what here actually have done, we are actually approximating each point locally and get the local fit. So for the local approximation, what we need to have some weight function corresponding to that particular point and some arbitrary support points. Here the blue dots are the support points. So in weighted RSM, to get the better fit, we perform the local approximation, or we are getting the local approximation best fit, and then we move for the global approximation, and in a way we are minimizing the error. So two things we need to very care about when we are dealing with the weighted RSM. First thing is we need to take care of the weights, then support point generation scheme. And we have talked about different kind of support point generation scheme. So here different kind of support point generation scheme are there. Like when we perform the response surface method, ordinary response surface method, we have used the support point generation scheme as mean first point, and then the other points mean plus minus k sigma. Here we have different kind of support point generation scheme based on our requirement, how we solve this problem. So here the code is very simple, and what is the difference we have already seen, and we already have seen the support point generations. So the code goes like this: you need to first have some support points and the weights ready for the particular problem. Once you have the support point generation scheme and weight are ready, you can perform either Monte Carlo simulation or the gradient based analysis on top of the prepared response surface method. So that's how the moving least square approach, you know, improve the fit over your ordinary response surface method. So that's all about actually moving least square approach, and we have already see the code how it works, and we perform some problems here. We have seen the Frank function and this problem also. I will update this code. You can modify it as per your convenience and your problem statements, and you can work out with that. Now let's move to the next topic, which is like stochastic response surface method. So up to this, Bob, do you have any queries or questions? You can ask me.
Thank you very much. Okay, for now, I'm following, so I
Okay.
need
So
time.
it's
Mm.
like if you understand the response surface method, weighted response surface is nothing but we are actually minimizing the local error by providing the best local fit. Like for this example, you just, if you can correlate this example, you can easily correlate the whole thing. First, we have all the points. Let me erase them. It's like uh not that tough, but like okay, it is not erasing. We have these points. If we first fit, yeah, it's giving me trouble, don't worry. I'll down it again. Just this problem, look at this problem. Like what in this problem, what we did first, if we don't introduce any points and we have these two data sets x and y, so just we need to, add that local uh, weight to this point, and we are getting the best fit locally. Look at this. First, this is the ordinary one and this one is the weighted. Now if we increase the weight 10
So,
to 100, yeah. So
how do you choose the weight?
how I choose, actually it is user defined. First we have seen, okay, this is the my fit response surface or fit polynomial. Now I have seen here, okay, this point is not properly approximated. So weights are basically controlled by the users. Here the arbitrary weight 10 are given. Now for the next problem 20 is given, right? 100 is given to get the better fit, but we have different kind of weight function. Based on that, these weights are defined for your particular problem. Like here we have seen different kind of weights, and during the code I also have seen that weights are there different kind of. Here these are the weight functions. So based on your problem, you need to figure it out which kind of weight you need to work with. So here during the code I have shown you, like here I have given one switch to control the weights. Like for my problem, which kind of weight will be, fit. Like here I have given the switch for the weight type 1. If the weight type 1, it will work out with the linearized regularized one. If 2, exponential, and so on. So these weights you need to figure it out for the particular problems and to check. And also the DOE, the design of experiments, like which kind of design of experiments you need to find it out. Like we have seen, when we use the rectangular design of experiments, we have this much of support points, and we are the simulation taking much time. Now when we change it to DYID 1, that means here the XCL one, it will calculate and run it, it will take less time, and it will generate less number of support points. So support points here you can see, if we use XCL, it will generate only this much of uh, support points. And also the results are similar, 2.89. And if we go for this DOID2, that means the rectangular one, So it will take more time because it is generating four number of kinds. In Excel it is generating less number of support points. So support points and weight, you need to figure it out. Like if I change the weight type, my result will change. So based on different kind of problems, you can choose the weight type. Now the thing is, catch is, we use the regularized one because the domain of influence for the regularized one actually, correlates with different kind of engineering problems. So these weights actually you need to figure it out for these particular points if you wish to fit it. Great. Like it is running, let it run. Like for this example, like this, if you see it closely, now see it. Now if I wish to fit this curve, look, this is your response surface, blue one. Can you fit the like in ordinary response surface method using linear, cubic or quadratic fit? No. So what we are doing, we are actually, approximating or locally approximating each points. Look, each points we are approximating, and we are providing different kind of weights as per my requirement. Then now I need to check it whether my weights and the support points are giving me the best approximation. If not, again trial and error. So these are the trial and error methods, and you need to choose the weights accordingly so that you will get the best fit at the end. Okay, like here we have
Okay.
seen in the previous example, we run the support point generation scheme is axial. Now we have the rectangular one. Here we have seen that we have large number of support points, so that my domain of influence is covered and the results also get improved. Last one was 2.88, now look 3.07, and this is close to our beta using form and sum 2.99999 something. So that's how you can control your weights and your support point generation schemes. Okay, it's completely
Okay.
based on the problems what you are dealing with. So here we are solving the Frank function. So already I have seen for the Frank function, either if I use the DOE as 2, that means rectangular, so it will give you plot like this, and we will have similar kind of results as shown by the instructor, right? So that's all. The weight and the support point generation scheme is the completely on the hand of the user. Okay, great. So
Okay.
that's all about response surface and moving response surface method. Now we have another sort of reliability or meta model based reliability scheme. So stochastic response surface method. Stochastic response surface method, here ordinary response surface method and moving response surface method, what we have used, we use the normal polynomial function like f of x is equals to a naught plus a1x plus a2x1, normal polynomial function. But we already have studied different kind of polynomial, and whom we call the orthogonal polynomials, right? On the last class we have went through the orthogonal polynomials. Now using that orthogonal polynomials instead of using normal polynomials, these orthogonal polynomials are helpful in a way that it reduces the number of simulations by their orthogonality property. Like when the I is equals to j, you will have values, otherwise you will have 0. That means in a way your number of simulation will be reduced. So this orthogonal, about the orthogonal polynomials, obviously we have seen on the last class. So quickly let's go through it. Then we will go that chaos based expansion. Like we have any orthogonal polynomial that should have some interval. So let's say we have the interval AB. Now what's, and it must have one leading term that defined by xi. So first the polynomial will be f naught x will be 1 because x to the power 0 will be 0. Sorry, 1. Now second, if we wish to find out the f1, so the leading term will be x to the power 1, and then we have a constant. This constant actually define the orthogonality between f1 and f0. That means 0th order orthogonal polynomial and first order orthogonal polynomial k1 naught. Now if we apply the orthogonality property with respect to some weight, what we will have, weight multiplied by these two. Look, I not equals to j, that means it will get 0. Now instead of f0 put 1, instead of f1 put this value, you will have this equation and solve it. You will have the constant 1, you have the constant, just put it back in your equation. This you will have your f1. That means the first order orthogonal polynomial. Now if continue the process, you will have nth order polynomial also. So the nth order orthogonal polynomial look like this. Fi will be x to the power I, ki0, f0, ki1, f1, and so on up to n minus 1. That means this constant will carry or move up to n minus 1 or I minus 1 order. So here the k you can find out. Now here I have introduced like j. Now Abdul, I hope now this equation is okay. Now 1 0 1 1 and so on. Like the first equation was little wrong, but now okay. I have introduced like first k 1 0. I if I wish to find, so just x to the power 1 and 0 0 1 k 1 1. I wish to find, just put 1 and 1 and all these things. So by this way, or you can figure it out how to find out these constants, basic mathematics. So this actually is the complete polynomial or complete orthogonal polynomial. Now the thing is, instead of normal polynomials, if we wish to use the orthogonal polynomial, we call stochastic response surface method. Now in orthogonal polynomials, we actually use Hermite polynomial in chaos form. Now what is that polynomial chaos expansion? Is nothing but the expansion of the polynomial. Like here you can see how much or how many terms should we consider during our analysis. The main question, how many terms we need to consider during our analysis. So here the chaos expansion, through the polynomial chaos expansion, we can actually control these things. And here for the polynomial chaos expansion and for the reliability problem, we generally use the Hermite polynomial, because the Hermite polynomial are defined with respect to the standard normal variables. Recall, in form, we need to convert our random variables to the standard normal space. So if we use the Hermite polynomial or the chaos of the Hermite polynomial, chaos is nothing but the expand form of your polynomial. Use that, so we can have the liberty to go to the standard normal space directly and solve the reliability problems. So how this polynomial chaos expansion based form work. So here you can see, like this was the actual multidimensional polynomial chaos expansion of the Hermite polynomial. Now if we compress this, look at this expression. It is look like your normal response surface expression, summation of I to 0 ai xi. So instead of the random variable, we have the Hermite polynomials. Now once we have this, like we can expand the series up to like first order, second order, third order. Here you can see order 1 will be this, order 2 Hermite polynomial, order 3, order 4. So these are actually chaos expansion of the Hermite polynomial. Now if we wish to work my problem with the order 1 polynomial, I will choose this and go with this term. Okay, now how this thing will work, I will show you. Like first step, when we need to use, like the first question should be like that, why we need to use that polynomial chaos base, or particularly Hermite polynomials, or orthogonal polynomials to solve our problems. So if we have the limit state highly nonlinear, or a limit state which itself contains some function, then for this case gradient based form might you know give the erroneous result. I haven't checked yet, but others says and literature says that okay, might give. So for this, you go for the polynomial chaos based expansion. Now how it does these things goes similar as your response surface method. Instead of normal polynomials, you need to use the polynomial chaos expansion, or particularly here we use that Hermite polynomial. So first what we need to do, we need to identify the function and variables which we need to approximate or substitute using PC. Then determine the order of PC, because the order of PC is very important. Here you can see, if you increase the order abruptly, there will be different or many terms arises during your calculation. So many times it might cost a higher simulation time. So you need to choose the order of the polynomial, and here we are using the Hermite polynomial, particularly the Hermite polynomial, because Hermite polynomial has the domain minus infinity to infinity, and these polynomials are defined with respect to the standard normal variables. That means we can directly have the access to go to the standard normal space directly. So once we have chosen the order of the polynomial. Now what we need to do? We need to determine the coefficient of PC. Now determination of coefficient of PC, here we can use either least square approximation or the moving least square approximation. So obviously we will go with the moving least square approximation, we will get better fit, or you can go with the least square approximation, or you can check these two also. Now once the response surface is ready or the limit state is ready, now we can go with form, SOM, MCS and all these things. So these are actually the steps for performing polynomial base chaos or polynomial chaos based form, like similar to your response surface method, but here instead of using normal polynomial, we are using or we are proposing to use like Hermite chaos as that basis function. That's all. Now how this will perform? First you need to identify which variable and function should be approximated by your PC. Then rest of the operations, like in form, if you need to uncorrelate the random variables, so correlate to uncorrelate eigen operation are same, and the transformation from your stand normal domain to standard normal domain, you first need to figure it out what I need to follow. Then you need to choose the order. Appropriate order is appreciated, because higher order will give you best result, but if you go for the higher order, you will have a lot of term, and that will cost computationally much. And if you go for abruptly lower order, that will also give the erroneous result. So basically we start with some order, and again iteratively we solve it. Now once this order and the basic variables are defined, then we need to find out the coefficients of the, like coefficients like unknown coefficients either we can use regression, that means least square approach, or the moving least square approach. Now once these things have done, what we have our limit state is ready. So instead of gz, we have g of, say, Hermite polynomial function. Right here, this is nothing but the Hermite polynomial. So we have now gz in terms of the Hermite polynomials. Now once we have the gz, we can have the gradients, like we can differentiate it. And once we have gradient, we can easily solve the gradient based form using Reckwitz or Reckwitz-Fissler algorithm. So here, once we have the gradients, we can solve for the beta, and once we have the beta using Reckwitz-Fissler algorithm, we can solve for the new design points. So the basic algorithm is similar to your uh, uh, response surface method, but some steps here we use instead of normal polynomials, Hermite polynomials are used. So first we need to define our basic variables, identify the basic variables which we need to replace by the PCE. Then you need to assume or fix some order of the PCE. Now evaluate the unknown of the PC. PC is nothing but the expanded form of your polynomial, and the polynomial in customized form. Here we are using the Hermite polynomial and all these things. Now we need to check, is it fit with the CDF or PDF that approximated we have done, is it fitting with that? If not, we need to again perform it, increasing the order. Now once we get the fit, that means approximated PDF or CDF fit with the actual PDF or CDF, then we go with form, SOM or other kind of like MCS kind of things, and we have the results. So here, like uh, during the course, this retaining wall problem was solved, so I will not go in details, but last I will just show 2 and 3 things. Like here the limit state is constructed with respect to the overturning moment, right? MR is the resisting moment, and MO is the actual moment which actually try to overturn the retaining wall on the side. So you can, now what first task is, you need to correlate this limit state surface with respect to the load you need to calculate, and finally we have this MR and M naught, and we have selected different variables. So these variables you need to select, or the variables you need to put randomness to it, you need to select. So here we have like 5 variables. First, case 1, for the case 1 we have assigned all normal, and for the case a different case we have assigned log normal and normal. Like you need to first identify the variable. Now see which distribution fits it properly. Either you have the idea, go with it. If you have don't idea, you have the statistical tool, like you have chi-square test, you have curve fitting test, you have your case test, perform it, check which distribution is fitting to your data, then you can propose this distribution also. So here a normal case and log normal and normal case are selected. So here the basic variables chosen like Q, surcharge load, wall friction, unitoid of soil friction, and unitoid of concrete. Now the covariance are already given. So first step was you need to identify the basic variables which you need to replace with the PC. So here my variables are these which I need to replace with PC. So here PC, I know this is Hermite polynomial chaos base form. So I need to approximate this. So here you can see we have approximated and check we are getting the best fit or not and perform the case one. So in case one, this was my GX. Look, GX is not completely or explicitly defined with respect to your basic variables, are they? But when we solve for MR and M naught, we will have the basic variables within it. Okay. Then, first we fix the B and vary that height. We just want to see that how with the height, how this beta will change. So this is the beta plot. We perform MCS, form and SOM. We see that, okay, all the results are similar. And here also the probability of failure for this 1.8 meter of B, we have seen that form, SOM and MCS has given same kind of result. That means the curvature correction are not required for this thing. That means it is not that much of highly nonlinear limited surface, so we can easily work it out. Now in second case, so we vary the B width and fix the height, because we have two parameter here, B and the height, total height H. So just for the check how much beta I am getting and how much PF I am getting. So here we can see that, okay, my MCS form PC, that means form polynomial chaos expansion, and SOM PC. SOM PC, after you solve form, you can go to the curvature correction either using Breitung approximation, or obviously you will go with Breitung approximation, and then you will get the second order corrections. In the second case, when we consider normal and log normal random variable, we are getting the similar kind of results. And we say, okay, this polynomial chaos based form are giving the closed results. Now you can ask the question. So when we have that form, normal form and MCS, why we go with that? And nothing. It's for your experience, for your research purpose. We have developed different kind of method, and we check. Okay, this is clear or not, this is clear or not. Like for the concrete, we decide, okay, the design period or design life is something 70 years or 8 years. Who told you that after 8 years concrete will get fail? And even till now humans don't know about the actual nature of the concrete. Like if we can for the concrete, if we can maintain it properly, most of the studies have shown that after 100 or 150 years the strength actually increase, because the hydration process is not stopped, and it is like continuing process. And until and unless how much it get hydrated, we don't know how much the CSH gel will produce, we don't know. Even from the that byproduct, CaOH, from that also CH can produce. So that's why we continuously try to develop something and check with the other ones, which one is getting better or giving the better results and not. And also obviously we have for the with the polynomial chaos based expansion, when we have highly nonlinear limited surface, it will give the good results. And your form gradient based result will erroneous give erroneous, obviously, because you can see that in polynomial chaos expansion we can easily control the order. And also if we wish to provide some weights for the particular points, we need to figure it out with that. That means in a way, if we follow this exercise and keep doing that trial and error method, one, we will get the ultimate converged result. That's all. Now after that, like higher order SRSM was introduced by UN all, like in 2008, that UN all introduced like higher order stochastic response surface. In ordinary stochastic response surface, what we do, we consider the GX as normal polynomial, then we solve for the coefficients, and then uh, response surface we solve with using that first order or second order reliability method, and ultimately to get the convergence we need to do the iteration. Now here in this paper in 2008 they have proposed the higher order polynomial term in this form, and they use instead of the Hermite polynomial they have used Chebyshev polynomial, different kind of orthogonal polynomial they have used, and they have tested it and shown that okay, using Chebyshev polynomial and using that procedure higher order polynomial you will get the better result, and your result will be close to your MCS value. Like here Chebyshev polynomial, Chebyshev polynomial have a domain -1 to +1. Here degree m lambda actually used for the search domain. Now the process are very simple. First you need to find out the Chebyshev polynomial. Here we have seen okay that Hermite polynomial, different kind of Hermite polynomial. Here also you can see first order, second order, third order, and fourth order Chebyshev polynomial, and the final version of Chebyshev polynomial is that some constant polynomial, some constant polynomial, some constant polynomial, and domain is +1 to -1. Here they have proposed some different support point generation scheme. Like here, first in SRM or stochastic the response surface method we have used mu plus minus k sigma. Here they have used okay, you should use this support point generation scheme mu plus some factor. This factor actually defines the sampling region and your sigma. That's all. And they have seen they have seen that okay, if you use this method and perform the reliability analysis you will get better result. Like here this example already taken from their paper. Here this is your response surface. Like similar kind of steps you need to perform. This is the polynomial version or higher order polynomial version what they have proposed using Chebyshev polynomial. Now you need to generate sample points using this, solve for this unknown coefficient. Once all these things are solved you will get your limit state surface or response surface in this form. Now here they have performed this response surface method and have shown like x1 and x2 they have chosen two normal standard normal random variables and seen that okay, here their higher order polynomial chaos expansion and MCS results are very close, while second order stochastic response surface method, that means using Hermite polynomials, will give the erroneous results. Look, till now we was like second order, third order Hermite polynomial will give us better result. In 2008 they come up with this higher order polynomial and shown that okay, if you have higher order of nonlinearity then you need to use this polynomial function or this as a function. So they have also tried okay, different kind of polynomials, and they have found that okay, for Chebyshev polynomial and using this method of support point generation, if you follow it you will get the better results. So in a way what we are doing, we are trying to find out some meta model or the response surface which will give the better fit and some weights and the support point generation scheme, because the approximation in a way depends on generation of support points and choosing the weight. Otherwise for the complex functions we cannot have the better fits or the best fit. Great. Now in adaptive association, again in a sequential manner we choose the support points. In a sequential manner we choose the support points. So here also like for this case, for the previous cases what we do, we have some support point generation scheme. In adaptive or the sequential process we have different kind of sequential support point generation scheme, like using sparse grid point generation scheme and all these things. So I will not go into details of this sparse grid type of things. So like it's a completely research domain. So rather I will discuss one civil engineering problem, how, where if one limit state is given in a explicit not given in explicit form, then how we can perform it. Like Bob, you were asking for this type of portal frame and how we can perform the reliability analysis when our limit state is not defined in in completely explicit form, how we can perform. So let's quickly discuss this portal frame problem. Okay, so like here we have this portal frame. So when you want to design which like you need to design it using some software. So for example, we have designed it using NSYS. You can design it using your stab or etabs and all these things. So here we have different elements, like 8 elements we have, and for different elements we have different kind of E, modulus of elasticity, I, and cross sectional. And we will consider all these as the random variables. And we have some lateral loads P1, P2, and P3, which are applying, which have applied on different story level. Now first what we need to do, we need to set our limit state. So here the limit state is set against the top deflection. So here for this particular node we are interested to carry out the reliability analysis. So we set our limit state y of x is equals to del naught. Del naught, that means the allowable deformation or deflection. So here this allowable one, either you can set as per your convenience, as per your requirement, or you can get it from IS code or your different standard code. Now del A actual, that means the actual deformation which is occurring at that point due to these loads. Now think, the deformation is not, or the deformations are not completely defined with respect to your E, A, I, and P, right? That means you don't have your limit state in explicit form. Now how you need to perform the reliability on this problem? Tell me, Bob. The big question, how? Because these all E, I, A, P all are random. Think all are random, not deterministic. How you will perform MCS on top of this structure? Tell me. So in a total, if we see, we have this 21 total random variables. 21 total random variables. But these random variables are not directly related to your GX. That means your GX is not completely defined with respect to these random variables. These are my random variables. You can see log normal, Rayleigh, and log normal and Rayleigh. Two distributions are there. E1, for E1 we have this, for E2 A, I we have. Now tell me how we can perform the reliability analysis for this kind of structure. Any idea, Abdul? How? The big question. We have a model ready in a NSYS or SAP or ETABS or MATLAB, sorry, or STAD. Now how we can perform this? And we have like 21 random variables. All are random. E, I, A, P, all are. These 21 are my random variables. Now how we can perform MCS? Bob, are you there?
Yes, yes, the
How we can perform? This is actually your problem. How we can perform this? While making the design, you need to put all these values. Like here, all the values, mean values and standard deviation are given. So first, you need to model
Data
it
point
using
generation.
the mean value. Listen to me. Mean values. Okay. Now, once you have the model ready, what you need to have, if you want to perform the MCS, you need to evaluate your GX, n times. That means the number of simulations, whatever you have prepared. Like you need to have 10 to the power 5 number of samples. That means YX, that means if write it down GX. You need to perform GX 10 to the power 5 times. How you will going to perform it? The big question. So it's very simple. First,
We will generate points, right?
what?
We will generate points, right?
Yeah,
For Monte
what
Carlo.
we can, how you can generate, you have your model in, say for example in NSYS, how you can generate and apply this again
Uh,
and again, again and
that,
again, again
that is
and again. So here, what you need to do, we need
awesome.
to, mm, merge our MATLAB and the finite element software in which you have done your modeling. And then in MATLAB, we are replacing those variable, calling them again and again. That means first we will generate the samples for these 21 random variables. And then say for example for P1, I have generated some sample. So first sample is 71 point this, second sample say 80. And another all kind of second samples. Now using that second sample, we can perform the static analysis and we can have this del. So for first test of sample, say for example, this del allowable is 0.9. minus in first sample we are having say 0.81. First run, in first run we can run it, right, using generating, say for p we have generated 100 sample, for p1 we have generated 100 sample, for 100 sample we'll get 100 del actual, 100 times we will evaluate it, store the result, again for p2 100 times, generate it, store the result, 100 times, generate it, store the result, completely you will get that much of samples. Now just count your how many times your gx is failed and total number of simulation you will get. That means you need to correlate, you need to assemble your that model with MATLAB, because in MATLAB you will generate the random numbers, then using that or random samples, pass this random sample to your this this model and evaluate your gx, evaluate your gx. For example, for here look at this mean value of p. So for example, for first p 71, second p 288, third p 133. Now I can generate 100 sample of this 3p, because I know the distribution, Rayleigh distribution, I can generate 100 sample of this p using this mean value and standard deviation. Now using that 100 sample, if I run it 100 times and check the deflection 100 times, del A 100 times. So 100 times we will get del X, 100 times we will get our GX. Yes or no? So I can check my probability of failure. Clear? So
Hmm.
this means, Bob, clear. So it will take time.
Yes, the function, how do you choose the function, whether it's a relay, whether it's a, because I've seen that the functions are chosen. How do you choose those functions?
Functions like this limit state function.
No, he's
No,
talking
go
about
to the next slide.
distributions.
Yes, the distributions.
Oh, this
Yes,
distributions, this
yes.
distributions, like you need to, like for the IA, what I said a few minutes back, if you don't know which distribution will fit to your data, what you need to do? You know the answer. What you need to do? Chi-square or case test, perform it, check it, or plot the histogram and check it which kind of distributions are there. For the concrete cube test, which distribution will you prefer, normal or log normal? For the cube test, which distribution you will prefer, or you will propose, normal or log normal? Tell me, Abdul or Bob, both. For the cube test, so cube test we
I'll
cannot
just
get the
I'll
negatives.
just normal.
Huh?
Normal.
No, the domain of the normal distribution is minus infinity to infinity, but
Strength.
will we have minus in cube test? No. So obviously go with the log normal,
Okay,
that
log
has
normal.
only
Oh,
the,
okay.
or you have the
Okay.
statistical tool I already have gone through, like case test, perform the case test or chi-square test, hypothetical test, or plot the histogram and try to fit one PDF and check which PDF is giving you better results. And for these parameters you have, in literature, for p, for e, for a, these are like log normal variables. And if you don't know, if you have some data set, if you don't know which distribution will fit, just go with the statistical test, you will find it out. Yes or no?
All right, that's right.
And mean value, you can have the proper value of a of this cross section mean. Now standard deviation you need to choose as per your requirement. Okay, or this thing. Clear, Abdul? How we can have this? So these are like
Yes.
no standard ones, like which, like we'll choose, like for a rainfall, we'll go with that exponential distribution. Sort of type 1 largest is also used for our civil engineering thing. So you need to figure it out for your problem which distribution you will going to propose. The proper distribution, you will get proper fit. Improper distribution, you will not get a proper fit. That's all. So how we are going to solve this problem? So we need to batch, we need to run the NCs in batch mode with respect to MATLAB. I will show you how we can actually perform. Actually, we will code this 7 or 8 story building. We'll actually have that 21 variables and we will run it. So here the limit state, how the limit state is performed, it's for the deflection. We are checking the deflection for the particular point. So we need to have this allowable we will have from our code, but the actual we need to have it from our model using that much of sample. That means you need to run your model static analysis. You need to run for the deflection. You need to run the static analysis for that much of times, and you will get it. So it's very simple code. You just need to merge these two code, MATLAB and your this. So for this purpose, you know, I prefer ANSYS mechanical FPDL, because the scripting thing is there and you can easily update the parameter. Like I want to update p3, how I can use update it? So if I write the model and if I know where exactly in which line the p3 is there, I can write a command, okay, replace the pc in second form like this value. So replacing this again and again, replacing this again and again, and run, replacing this again and again, and run. Get it? So we will precisely do it on 12th week. We'll show you how we can do this. We will make the model in complete model in mechanical FPDL, and we will link it to MATLAB, and we will run it. We will get this uh, thing. Because for the cases when we will perform, we are going to perform the reliability analysis. We are talking about like models. So we need to run it in a batch mode. In a single go we cannot do it, because we need a hell lot of samples to validate our models and to get the results. So it's very simple. Go with Workbench or APDL, and try to run it batch made with the MATLAB, and precisely we will do that. So that's all. So response surface and stochastic response surface method. Like now you can check, you can say, okay, using these distributions, and if we perform all these things, we are getting here MCS. We are looking for MCS. We are getting the value, this probability of failure. So that will be my probability failure. Here the del allowable is taken as 0.025. You can take this allowable deflection as per your code. You have some code, ACI code, we have Indian standard code, we have allowable deflection for the top story, or we have allowable deflection for serviceable limit state condition, and allowable deflection for ultimate limit state condition. So based on that we can perform it and we can check the results. We will precisely do it. So that's all. So let's quickly go through our assignments and all these things. So have you solved the assignments?
Not this time.
Yeah. So select the expression for first order and second order Hurwitz polynomial, where a, I, j are the polynomial coefficients. Look, you have already in our PPT. Where are you? Here. So first, second order. Just select two. Clear. Now go to next problem. These are interesting thing, but we cannot cover all these things, or we don't need actually all these things for our cases. Now here the second question. So first question will be these two, a naught plus a1 z1. The second one, a naught plus aij plus aii zi square plus this. That will be two expression for first order and second order. Now this, if let f of x, okay, for here moving least square approach. So moving least square approach, you just need to multiply weight and weight. It's a very simple. Like then which expression will be used to find out the values of coefficient a using moving least square method? So here nothing but this f, x and w are the original function, polynomial set and weighted matrix. So obviously a will be nothing but x transpose w into x inverse, x transpose w into f. And ordinary least square method, we don't use the weight function. Like ordinary, if you wish to solve it using ordinary least square method, a will be nothing but your x transpose x inverse x transpose f. And here for the moving least square method, we need to introduce weight. So this will be your correct answer. Now let's go to the third. Select the correct statement about the design of experiment. According to Khosal's design, the minimum number of support point is 2. No. Khosal design, we have seen the minimum number of support point is 3. So this is wrong. According to the Khosal design, the minimum number of support points for the linear basis is 3. Yes, this is right. According to the full factorial design, the maximum number of support point for the linear basis is 4. Yeah. This is also right. According to the full factorial design, the minimum number of support points on linear basis 6. No, this is 3. So look at the support point generation scheme. That means device. Here we have the device. In causal design, we have linear basis 3, quadratic basis 4. So these two things are right. Like, let's see quickly. Yeah. In causal design, we can see the minimum number of support point generation is 3 for the linear basis. For the quadratic basis, we have the 3, 4, 5. So this, and for the full factorial design, minimum support points are 4 and maximum support points are 6. So that means our B and C will be correct answer. Yeah, B and C. According to the full factorial design, the maximum number of support points on a linear basis 6. No, this 4. So B and C will be the correct answer. Okay. Now find out the proposed higher order stochastic response surface given by a surface given by Gavin and you. Given by Gavin and you. What was that? This one. Just go through the paper. You will see there is only higher order polynomial given by this. Okay. Now select the correct statement about Chebyshev polynomial. Again on this slide you will get, because they worked out these higher order polynomial things using Chebyshev polynomial. So the interval of the Chebyshev polynomial is -1 to 1, and the weight function for the Chebyshev polynomial is actually 1 minus x squared to the power half. And for the Hermite polynomial, this weight function is nothing but the standard normal variance. Standard normal distribution, nothing but that. Now select the correct statement. Hermite polynomial is continuous function of random variables. Hermite polynomial is a continuous function of random variables. Yeah, you can say it, right? Okay. Now Charrier polynomial is a discrete function of random variable. Okay. We need to see it. Support range of Hermite polynomial is no. Hermite polynomial range is -infinity to infinity. This one is right. This one is also right. Now take later this one. Charlier polynomial is a discrete function, discrete or not. So we have a table, right? You don't need to remember these things in final exam. These things I think this will not come, but on the 12th week we will discuss particularly on the final thing. So Charrier, yeah, is the basic function is Poisson is discrete. Okay, it's also
Actually, I'm worried about the final exam because I don't know how can someone memorize these equations or keep all the.
no. I will discuss exactly what type of problems will come or going to come you using your final examination. I will discuss it, and this will be very easy. Like, you
Okay.
don't need to remember anything. All the equations will be provided. All your normal table also will be provided in your book. So you just need to sit with me for 1 and 2 hours. So on the 12th week we will precisely do that. Great.
Thank you.
What tricks you just need to
Abdul, you are
remember?
right.
Yeah, remember. Otherwise you cannot remember all the things. What your course
At
instructor
all.
cannot remember this. So I will discuss what kind of questions will come and how you will approach it, and all the formulations, all the things will be given. Like I will discuss similar kind of problems which are going to come in your examination on the 12th week. Precisely we will do that. Okay, now like select the correct statement about the weight matrix. The weight matrix actually is a diagonal matrix. The C will be the correct answer. Now the following step, polynomial chaos based form. So recall, in polynomial chaos based form, first we need to identify the function and variables based which we need to replace by PC. So 2 number will be the first. Then second will be we need to find out the order of the PC. That means 4. That means the correct answer will be D. Then we need to evaluate the coefficient. Then we need to perform the form. So correct answer will be the D. Now here select the correct statement. The response surface method aims to replace the original failure function by an equivalent function. Yeah, this is right. Right or wrong? Right. The response surface method is more computationally efficient than Monte Carlo simulation. The response surface method is more computationally efficient than Monte Carlo simulation.
This should be true, right?
Yeah, it should be true. It
Uh-huh.
should be true. It should be true. It should be true. Yeah. The response surface is more computationally efficient than the Monte Carlo simulation. Yeah. We can say it. We can say it. Okay. Now the Monte Carlo simulation is more computationally efficient than response surface method. Select the correct statement. The Monte Carlo simulation is more computationally efficient. Computationally efficient, not. For the first approximation, the last one is wrong. So A is the correct answer, and like the B will be the correct answer, not C.
Okay. Okay.
Sovik, Sovik. Okay. So A and B. So not A and C. Monte Carlo simulation is more computationally efficient than response surface method. We cannot say it. So like one and two, and these are like contradictory statements. We cannot say it. Yeah. So we like this question. Just remember this question. Choose the correct statement. Okay. Correct statements. Okay. Now A and B. Initially A and C was chosen. So what do we need to do? We need to either drop it or change it accordingly. I will talk to you. Now, Chebyshev polynomial, for the Chebyshev polynomial, if we have degree m and lambda, so it's nothing but the Tm is defined by this. You will just get it. So, okay, that's all the questions for today. But this thing, okay, these two are the contradictory statements. We cannot say it. Monte Carlo simulation is more computerly efficient or less computationally efficient than response surface method. Like in general, we cannot say it. If we have, but the second statement, the response surface method is more computationally efficient than Monte Carlo simulation, we can say it. So let's, okay. So do you have any other queries? Otherwise, we
Yeah,
can,
I believe we left one question. Maybe,
yeah,
maybe I just missed it out.
yeah,
It is regarding the select the correct statement. It is question number 9 in this time's assignment, this week's assignment.
okay.
So there are four statements.
Hmm.
I haven't gone through it, but one says a stochastic response surface method is the summation of orthogonal polynomials
Okay,
described in terms of random variables. This is
yeah,
option number one.
okay,
The second option is stochastic response surface method is the multiplication of orthogonal polynomials described in terms of random variables.
great.
Option
Hmm.
Option 3 is the minimum number of required support points is dependent on the number of random variables and considered order of the orthogonal polynomial.
Okay,
Third option. Now, the final option is the minimum number of required support points is only dependent on the considered order of the orthogonal polynomial and independent on the number of random variables.
okay,
We left
okay,
this.
okay, okay, got it, got it, got it. Like I need to see the question, then I just show you the solution. Like check it. You told that four,
It's question number 9.
nine, right? Okay, this one.
Yes.
Yeah. Yeah, the stochastic response surface method is a summation of orthogonal polynomials, right? You can say it because we are using the Hermite polynomials as a basis function and we use for them. This is right
Yeah.
also. Stochastic response surface method is the multiplication of orthogonal polynomial. No, is summation of actually. The minimum number of required support points is depends on the number of random variables and the considered order of the orthogonal polynomial. Yeah, this is right. The minimum number of support points. This is right also. The minimum number of required support points is only depend on the considered order of the polynomial. No. So A and C will be the right answer. Yeah, this okay. A and C. Do you have any
Thank
doubt
you.
regarding it?
No,
No.
no, no, no.
Like a summation of this A and the like C, the minimum number of required support points depend on the random variables and order. How many, order that order you have considered and the random variable also there. So this A and C will be the correct answer. Okay, great. Then Bob, do you have any doubts? Then otherwise we can conclude here.
No, I'm fine. I just have to go through. Sorry, last week I was in the US, so I wouldn't get time to
Yeah, yeah, no
attend the
issue. You just
lectures
go
there.
through it. Like
Yeah.
for the course this, but for further like for mm, research purpose, if you wish to integrate any of the uh, scheme of reliability analysis, and you if you fail anything like okay, you need any kind of help, so just contact me, no problem. We can figure it out. Okay. And I also interested. I also uh, mm, grown some into. I have grown some interest on this subject, so I will definitely work on this field. Want to work. Okay. So that's all. We will meet again on
All right.
next Sunday. I feel 1 week left, and there we precisely do the you know mm, factor of safety based design, and how we can choose these factor of safety formats, and all these things we will see. And on the last class we will precisely do the that question, because this is the main thing. Yeah, obviously with that question, that means I can tell you, when we are setting this question, the first thing, like how we can set something that with that course one, without calculator, without MATLAB, uh, and with an on-screen calculator, can actually solve and that kind of problems actually we will discuss it. No issue. So for now, okay.
All right.
Okay, so
All
thank
right.
you.
Thank you very much.
Yeah, so
Thank you.
I'm ending the call. Thank you.
All right. Bye bye.